Hello everybody and welcome to this video. My name is Raman Mab. It's my great pleasure to share with you this presentation and talk on an extension to the Collatz conjecture. This work was recently introduced by Abderrahmane Bouhamadi, a mathematician from the University of Calais, France. This work was published by the author as a preprint on Archive in 2026 and HAL in 2023. This presentation is divided into three parts. First, I will briefly recall the classical Collatz conjecture. If you would like more background on the original problem, there are already plenty of excellent YouTube videos that explain it perfectly. Next, we go through a particularly interesting example of this extension conjecture. As we will see, it's a very interesting alternative to the classical Collatz conjecture, as a process modulo 10, while the classical Collatz conjecture may be seen as a process modulo 2. Finally, I will examine with you, in detail, the general, the extended and unified conjecture introduced by Bouhamadi. I hope that you will enjoy with me this presentation. It will take about 25 minutes. At the end of this video, you will be able to generate many examples and maybe many illustrations. So, let's get started. Collatz conjecture, a famous and very simple conjecture in mathematics. This conjecture is very easy to formulate and easy to understand, but it's very hard to prove. Since 1937, this conjecture resists to great mathematicians in the world. Mathematics are not yet ready for such problem, Paul Erdos famously said about the Collatz conjecture. The classical Collatz conjecture can be formulated as follows. Choose any positive integer n. If n is even, divide it by 2. Otherwise, multiply it by 3, add 1, and divide the result by 2. Repeat the process iteratively. This is the accelerate form of the Collatz process. The conjecture states that, regardless of the starting number n, the repetitive process eventually reaches 1 in a finite number of steps. For any positive integer n, the trajectory starting from the integer n eventually enters the cycle 1, 2, 1. The associate map to this process, denoted by C, as in Collatz, may be given as C of n equals n divided by 2 if n is even. C of n equals 3 times n plus 1, all divided by 2, if n is odd. The Collatz conjecture may be formulated with mathematical symbols, as follows. For any integer n greater or equal to 1, there exists a positive integer k such that the iterate by c of order k equals 1. Here, you can see some fascinating visual representations based on the Collatz process. For example, a graph generated by the process. Several trajectories starting from different initial numbers. A 3D graph resembling a tree, where the fruits represent numbers. As you can see, one can create many different representations and animations using the Collatz process. The Collatz conjecture is so intriguing that a Japanese organization is offering a prize of 120 million Japanese yen to anyone who publish a proof to this conjecture in a top of mathematical journal. It is a massive prize for one of a mysterious problem in mathematics, a puzzle that remained unsolved since 1937. While the ultimate proof remains out of reach, mathematicians have spent decades building solid results around the problem. For over 80 years, the Collatz conjecture has stood alone. A mysterious mathematical island in the vast ocean of number theory and discrete dynamical systems. We've studied its simple rules. It remains disconnected from any larger framework. But what if this sequence is just a tiny fragment of a much larger, hidden mathematical universe? What if the Collatz map is not a unique phenomenon? but merely the origin of an infinite family of maps, each generating its own cycles? In this video, we are going to introduce a fascinating extension of this famous conjecture. This work, as we said before, is recently published by Abderrahmane Bohamedi from the University of Calais in France, provides a new perspective on these dynamical systems. We call it the family of maps. T, P, Q. A generalized system, where the original Collatz conjecture is simply the ground state, the point, where both P and Q are zero. To see how this works, let's look at a compelling example. When we set P to 3 and Q to 1, we move beyond the binary case. While the classical Collatz process operates modulo 2, this new system, with parameters 10, 12, and 8, unfolds as a process, modulo 10. But this generalization raises profound questions. First question: do the maps TP, Q have cycles? Second question: how many cycles are there for each map? And third question: are all trajectories under these maps bounded? And do they eventually reach a cycle? In this video, we are going to explore the answers to all these questions and uncover the hidden architecture of the TP-Q family. An interesting, particular example from Bohamedi's conjecture is the case of the conjecture modulo 10. This occurs when the parameter P equals 3 and the parameter Q equals 1. The rule for this system is simple and easy to formulate using basic vocabulary. Choose any positive integer, n. If the number ends in 0, divide it by 10. Otherwise, multiply the number by 12, add 8 times the last digit of n, and divide the total by 10. Repeat the process iteratively. This particular conjecture posits that starting with any integer greater than or equal to 1, the trajectory is always bounded, and eventually reaches the number 4. For this system, all trajectories flow into the trivial cycle 4, 8, 16, 24, 32, 40, which then leads back to 4. The map T associated to the process corresponding to P equals 3 and Q equals 1 is mathematically defined as follows. If n is a multiple of 10, T of n equals n divided by 10. Otherwise, T of n equals 12 times n plus 8 times the remainder of n divided by 10, all divided by 10. The particular conjecture may be stated in mathematical symbols as follows. For any n greater or equal to 1, there exists a positive integer k such that the iterate of t of order k equals 4. Let's look at a concrete example to see the process modulo 10 in action. Just to explain how it works. Suppose our starting number is 27. We multiply 27 by 12, add 8 times 7, and divide by 10. We get 38. Next, 38 times 12 plus 8 times 8 divided by 10 gives us 52. Then, 52 times 12 plus 8 times 2 divided by 10 gives us 64. (64 times 12 plus 8 times 4 divided by 10 gives us 80. 80 ends in 0. So, we divide by 10 and we get 8. 8 times 12 plus 8 times 8 divided by 10 is 16. 16 leads to 24. 24 leads to 32. 32 leads to 40. And 40 divided by 10, so the trajectory reaches 4. Now, let's look at the complete trajectory, starting from 27. 27. 38. 52. 64. 80. Then, we reach 8. And here, we enter the cycle. 16, 24, 32, 40, 4, and back to 8. The loop is closed. Let us now see some illustrations and visualizations. We can see here several trajectories, starting from different integers. Just like the classical Collatz conjecture, all these paths eventually converge toward the same attractor. Here is A. (3D representation, visualizing the trajectories as branches of a tree, where numbers are like fruits, growing toward the root. Whether we use animations or curves, the result is always the same. A beautiful, structured collapse into the trivial cycle. Some animated curves, showing the trajectories, stating from different integers. Let us now examine a simple Python script. We will write a simple Python script to compute the trajectory of a given integer n. First, we define the nextTerm function which, as its name suggests, this function computes the next term for an input integer n. This function is coded to strictly follow the mathematical definition of the map T. Then, we define the trajectory function. This generates the trajectory as a list, starting from an input number n, and stopping when it reaches the number 4. We use a while loop to continue the calculations until our variable m equals 4, storing each step in a list called traj. Note that in the trajectory function, there is no limit on the number of iterations. If the trajectory of an initial integer n never reaches 4, the while loop will run infinitely. After that, we use print statements to output the resulting list of trajectories for our starting number. As you can see, we have tested the code using both small and large numbers. Notice that, for all our tests, the sequence eventually reaches 4. For a large number, the trajectory may also be very long. It reaches 4 after more than 1,000 steps, and perhaps even more. Finally, we generate a graph to visually illustrate these trajectories. I encourage you to pause the video, copy this code, and experiment. What happens if you try a number with 100 digits? Feel free to experiment and improve the code using your own imagination. To verify the stability of this conjecture, we didn't just test small numbers. Using high-performance computing, this modulo 10 conjecture has been tested for every starting integer, up to 2 to the 45th power. That is over 35 trillion numbers. Even at this astronomical scale, no counterexamples were found. Every single trajectory, no matter how high it climbed, eventually fell back into the same cycle, 4, 8, 16, 24, 32, 40. This massive numerical evidence suggests that the system for p equals 3 and q equals 1 is just as robust as the original Collatz conjecture, but it operates in a much wider, digital landscape. In the next part, we will see that this is only the beginning. Modulo 10 is just one star in the infinite T, P, Q galaxy. In this last part, we will present the unified and general map T, P, Q that encompasses the classical Collatz map C, together with the map T. The answer to the three questions is formulated by Bohamidi as a general conjecture. To understand the heart of this research, we must look at the parameters that define this new landscape. The author introduces two positive integers, p and q, where p is always greater than or equal to q. From these two values, the entire system emerges. The divisor, d, is the sum of 2 to the power of p and 2 to the power of q. The coefficients, alpha and beta, are then derived from this same logic, ensuring a perfect modular balance. This defines the mapping T, P, Q, where for any integer n, the result is always an integer. If n is a multiple of d, the map simply performs a division, reducing the value's magnitude. But when n is not divisible by d, the mapping applies a specific linear growth. The formula, alpha times n, plus beta times the rest in the division of n by d, all divided by d, ensures that the output is always an integer. We use the notation, bracket n sub d, to represent the remainder of the Euclidean division of n by d. The definition of the map T, P, Q is a crucial property. It preserves the integrity of the discrete dynamical system. By tuning the parameters p and q, the author has transformed a single numerical path into a structured family of trajectories. In this framework, the original Collatz conjecture is merely the starting point, where p and q are both 0. And if we set p to 3 and q to 1, we obtain the modulo 10 system we just explored. By expanding to any p and q, we discover a vast landscape of discrete dynamical systems. Through this generalization, we could potentially gain a deeper understanding of the conjecture's underlying structure. By stepping beyond the narrow path of the original problem, we may perhaps see the hidden architecture that governs these numbers, the power sum divisor, the multiplier, and the increment. Mathematics often reveals its deepest secrets through the lens of generalization. As the mathematician Richard Collatz said, the map T, PQ may be written as given here. We can simplify the definition of T, PQ as given in this formula. We can observe that if the difference p minus q is a power of 2, such as 2 to the power of r, for some integer r, then the divisor integer may be seen as a Fermat number. We have the boxed formula written in blue. The detailed proof of this formula may be found in the paper of Bohamidi. Large omega of small omega is a notation for a cycle starting from an integer small omega. The trivial cycle is given by its starting integer, together with its length. As a consequence, for all positive integers p and q, such that p is greater than or equal to q, the map T, P, Q has at least the trivial cycle, starting from 2 to the power of p minus q. As you can see, the trivial cycle is explicitly given here. Now, you can see some examples of the trivial cycle for different values of the parameters p and q. The unified conjecture may be formulated as follows. For all positive integers p and q such that p is greater than or equal to q. First, if the couple p, q, does not belong to the exceptional set E, then the map T, p, q, has exactly the trivial cycle as the unique cycle. Second, if the couple p, q, belongs to the exceptional set E, and is different from the couple 5, 2, then the map T, p, q, has exactly two cycles, the trivial cycle, and also a secondary cycle starting from the integer omega sub p, q. And finally, the map T, 5, 2, has exactly three cycles, the trivial cycle, and also two other secondary cycles. All the trajectories are bounded and eventually reach an element of the attractor set A, P, Q. The attractor set A, P, Q, and the exceptional set E are given explicitly by the written formula. As you can see, all the elements omega, p, q are given in the table you are seeing on the screen. As you will see, all the secondary cycles are explicitly known. At the end of this video, I will show you a Python code and also a simulator, in which all the secondary cycles are explicitly given. Just for illustration, we show you some examples of trajectories for different values of the couple p, q. Now, to give some numerical analysis of the basin attractor when we have a secondary cycle. We may ask this question. Which cycle attracts more integers? We give the answer as a percentage for the starting integers up to 10 million. For different cases, we have the percentage of the basin attractor. As we can see, the trivial cycle attracts a higher percentage of elements, except for the case p equals 1 and q equals 0, where the secondary cycle attracts a larger percentage of integers. The unified conjecture was tested by computer until pmax equals 20, for all integers n up to 10 to the 9th power. This is about more than 200 billion trajectories. Let us now show you some curves representing the trajectories for different values of p and q. We observe that the trajectories always reach the basin, according to the unified conjecture. You can also see many different graphs representing the process for some different values of the parameters p and q. As you can observe, for a couple p, q, belonging to the exceptional set E, we have secondary cycle, so the graph of such corresponding process is not connected and the process is represented by two graphs or three graphs in the case of the couple 5, 2. As in the previous part, let us now examine a simple Python script. We will write this code to compute the trajectory of a given integer n for different values of the parameters p and q. This script will be slightly different from the previous one, though we follow the same directives. First, we define the nextTerm function. As its name suggests, this function computes the next term for an input integer n. The function is coded to strictly follow the mathematical definition of the map t, p, q. Then, we define the trajectory function. This generates the trajectory as a list, starting from an input number n, and stopping only when it reaches an element in the attractor set A, P, Q. In the code, this set is simply defined as A. Next, we define the exceptional set, E, as a dictionary, according to the table previously shown on the screen. From this set E, if the tuple P, Q is found within it, the code automatically updates the attractor set. As in the previous code, we use a while loop to continue the calculations until our variable m belongs to the attractor set A. Each step is stored in a list called traj. Note that in this trajectory function, there is no limit on the number of iterations. If the trajectory of an initial integer were to never reach the attractor, the while loop would run infinitely. After that, we use print statements to output the resulting list of trajectories for our starting number. As you can see, we have tested the code, using both small and large numbers for different tuples, p, q, and notice that, for all our tests, the sequence eventually reaches the attractor set A. For a very large number, the trajectory may be quite long, reaching the attractor after more than 1,000 steps, or perhaps even more. Finally, we generate graphs to visually illustrate these trajectories. Just like with the previous code, I encourage you to pause the video, copy this code, and experiment. What happens if you try a number with 100 digits? Feel free to experiment and improve the code using your own imagination. To help you visualize these dynamical systems, a dedicated online simulator is available on GitHub pages. Let us see how it works. First, you choose your parameters p and q. For example, if you input 3 and 1, you will recover our famous rule of 10. As soon as you set these parameters, the simulator automatically generates the specific conjecture statement. It tells you the exact number of expected cycles and displays their values. Next, you enter your starting number n and click on Simulate Trajectory and Draw Graph. The tool instantly calculates the steps and renders an interactive visualization of the sequence. You can zoom in on the graph and even export it as a PNG or SVG image. Please note that this educational tool is not optimized for extremely large numbers. I invite you to explore this mathematical universe on your own. You will find the link to the simulator in the description below. As a conclusion, the unified conjecture introduced by Bohamidi has been explained in detail, with many examples, animated trajectories, and illustrations. First, we explained how the map T, P, Q works. After that, we exposed the main unified conjecture, and we explained the attractor set, together with the exceptional set, E. Many challenging questions arise from this study. Challenge 1. The quest for order 4. Is it possible to find a pair, P, Q, with 4 or more distinct cycles? Challenge 2. Is it possible to find a secondary cycle, with a length of more than 630 steps? Challenges 1 and 2 may be said in other words, is the exceptional set, E, complete? The ultimate challenge remains. Prove, or disprove, the general unified conjecture. You can also code this unified conjecture, and explore it by computer. Maybe, you will be the one who disproves it. I hope that you enjoyed this presentation. Please, let me read your comments and remarks on this work introduced by Bohamidi. Thank you very much for your attention.